Hi everyone, and welcome to this hands-on, end-to-end Databricks real-time streaming ETL project with Delta Live Tables, or DLT as it's abbreviated. In this project, we'll build a complete streaming pipeline on DLT. It will consist of streaming tables, materialized views, stream-to-static joins, stream-to-stream joins, window aggregations, and watermarking. The project is comprehensive. It covers multiple topics which should enable you to level up your skills and create production-grade ETL pipelines using DLT. The target audience for this project would be data engineers and analytics engineers, and I would put the difficulty level between intermediate to advanced. To get the most out of this project, you should be familiar with the Databricks platform, and this includes Unity Catalog. You should be comfortable writing Python and PySpark for both batch ETL and Spark structured streaming. I'll personally be doing the demo on Azure Databricks, but any premium Databricks workspace with Unity Catalog enabled will work. Now, before we begin, as a side note, if you need any foundational structured training, then feel free to check out my Udemy courses. Links and special discounts are in the description below. I have a range of Databricks courses, including Azure Databricks for data engineering, analytics engineering with DBT, and CI/CD with Databricks Asset Bundles. Okay, great. Now before I go over the detailed solution architecture, let me give a quick overview of some DLT basics. DLT provides a fully declarative API, letting you define tables and transformations with simple decorators and SQL-like commands instead of writing imperative Spark streaming code. It focuses on what needs to be achieved, leaving the underlying system to determine the best way to execute the task. In simple words, you declare your tables with Python or SQL decorators, and then under the hood, DLT automatically handles incremental processing. For streaming tables, incremental processing is built by design. For materialized views, DLT provides an incremental processing engine. To use it, you write your transformation logic with batch semantics, and then the engine will only process new data and changes in the data sources whenever possible. Automatic orchestration. DLT figures out the dependency graph and runs everything in the right order, in parallel wherever possible. If a task fails, it retries at the task level, then the flow level, then the whole pipeline. No extra retry code is required. Data quality. You embed your data quality expectations directly alongside your transformations. Bad records are quarantined or rejected before they ever reach downstream tables. With DLT, you spend your time modeling your pipeline and business logic, and the framework takes care of reliability, monitoring, and performance optimizations for you. Let's walk through the core concepts of Delta Live Tables. A flow is the foundational data processing concept in DLT, which supports both streaming and batch semantics. A flow reads data from a source, applies user-defined processing logic, and writes the result into a target. Streaming tables are Unity Catalog tables that receive one or more streaming flows and continuously ingests new data. A materialized view is a form of Unity Catalog managed table, and it's a batch target. A materialized view can have one or more materialized view flows written into it. A sink is a streaming target for DLT, and currently supports Delta tables, Apache Kafka topics, and Azure Event Hubs topics. A sink can have one or more streaming flows written into it. Pipelines tie it all together. You declare your flows, streaming tables, materialized views, and sinks in code, and DLT automatically infers dependencies, orchestrates execution, handles retries, and scales infrastructure for you. For more information, please refer to the official documentation, which I'll share in the course description. Now that I've provided some context into DLT, let me give a high-level solution overview for the project. We'll be working on a real-time streaming scenario. In this scenario, we're simulating a structural health monitoring system for 5 major European bridges. We're analyzing data from IoT sensors mounted on these bridges. Each bridge contains 3 sensors. Each sensor streams 3 key metrics every minute: ambient temperature, deck vibration, and tilt angle. By continuously aggregating and correlating these readings, operators can detect unusual spikes or creeping lean in near real time. Here's how it comes together. We'll be implementing a medallion architecture on Unity Catalog, from landing for the source data, bronze for the raw data, silver for the enriched data, all the way through to gold for the aggregated business-ready data. First, we need to simulate realistic live stream data for our bridge sensors. To do that, we'll run a Python generate stream function, emitting readings every minute per device in a loop. We'll deliberately offset each event's timestamp by a random value between 0 to 60 seconds to mimic real-world network or processing lag, so our pipeline will learn to handle slightly out-of-order arrivals. This mimics a real-world scenario because there can always be unforeseen delays in receiving the data. Each batch of synthetic readings is simply appended into its own delta table in the bronze layer, giving us 3 independent, continuously updating streams to feed into silver and gold. In the silver layer, we first materialize a static bridge metadata table, mapping each device ID to its bridge name, location, and other characteristics. Then, for each raw bronze stream, bridge temperature, bridge vibration, and bridge tilt, we define a streaming silver table that applies simple data quality checks via DLT expectations and performs a stream static join against the bridge metadata static table, so each reading in the silver table carries the bridge name and location that it relates to. This gives us 3 clean, self-describing streams, with metadata attached, and any bad rows will trigger a warning or be quarantined. In the gold layer, we bring everything together in a single consolidated table. In this layer, we're computing 10-minute aggregates of the readings. For each bridge in the incoming stream, we calculate the average temperature over the 10-minute window, the maximum vibration recorded in that same window, and the maximum tilt angle recorded in that window. We apply a 2-minute watermark to accommodate the intentional timestamp lag at the source. This lets us include any slightly late events before closing each aggregation window, while still bounding state and dropping anything that arrives beyond that delay. We then join the 3 aggregated streams together on the exact same keys: bridge ID, window start, and window end. This stream-to-stream join ensures that each output row contains all 3 metrics for the same bridge and interval period. The final result is an append-only, production-ready table with 1 row per bridge per 10-minute window, delivering a unified view of temperature, vibration, and tilt for real-time monitoring. Let me clarify that all of the tables, except for the bridge metadata table, are streaming tables, and the entire DLT pipeline is incremental. It only processes new or changed data. Now that we've covered the project overview, let me walk you through my setup. I'm running this demo on Microsoft Azure using a premium tier Databricks workspace called DBW Trial UK South. Azure offers a 14-day free trial for premium Databricks workspaces, which includes serverless compute at no charge. Just be aware that storage usage still incurs fees, so keep an eye out on your account and monitor your costs if you're following along. When you create a new Databricks workspace on Azure, under the pricing tier, please ensure you select the trial. This will give you 14 days free DBUs when it comes to serverless compute. Once your workspace is provisioned, click on Launch Workspace. You should verify that Unity Catalog is enabled on the workspace. So go to Catalog, click on this cog, and then you should see that the workspace is assigned to this metastore. So for you, it will just say your specific region. Because mine is UK South, it's created a metastore in the UK South region. You'll also need to ensure that the serverless feature is turned on. To do that, you need to go to your account console. So click on this drop-down, go to Manage Account. Under Settings, Feature Enablement, please ensure that serverless compute for workflows, notebooks, and Delta Live tables is enabled. If it isn't, then make sure it is, and you'll need to refresh your Databricks workspace for the changes to take effect. Next, in the Catalog Explorer, I've created a catalog called Bridge Monitoring. This is the catalog for the project. It contains 4 schemas. Please make sure you create the catalog and the schemas. They're called 00 Landing, 01 Bronze, 02 Silver, and 03 Gold. In the landing schema, I also have this streaming volume. So this is a volume. You can see it in the schema if you go to volumes. So this is a managed volumes. The volume contains 3 empty subfolders: bridge temperature, bridge tilt, and bridge vibration. This is where our synthetic data generator will write the raw Delta files. Make sure you've created the catalog, schemas, and volume structure before you start the project. All of the notebooks and source code for this project are in this GitHub repository. Just fork the repository and then link that repository to your Databricks workspace. I'll drop a link in the video description. Let's switch back over to the Databricks workspace, where I'll run through the project code. All of the notebooks and scripts that you see in this workspace folder are synced directly from the GitHub repository that I linked in the description. So here are all of the notebooks. I'll start by explaining this notebook, 00 Data Generator. The notebook can be run manually and independently of our upcoming DLT pipeline. It continuously simulates 3 IoT streams: temperature, vibration, and tilt, writing the data to the storage volume in the landing schema. So if you recall, if I just open this in a new tab, here is the landing schema, and then we have got this volume in the landing schema. And then we've already created 3 empty subdirectories where this data generator will write synthetic data. So in the top cell, I'm defining a function called generateStream. This function is a reusable data simulator that continuously emits synthetic IoT readings into that storage path. We're importing all of the relevant modules in these 2 lines. And then, as you can see, the function itself takes a number of arguments. The path should be the Delta file system location where each batch is appended. The column name is the metric that you're simulating. So in our case, this will be temperature, vibration, or bridge tilt. It will store the readings into a column of the same name. Low and high are numeric ranges for the column metric's random values. For example, if low is 0 and high is 20, and the column name is temperature, then there will be a temperature column which only contains values between low of 0 and high of 20. Device count is how many distinct sensors to generate per batch. The batch interval _s is how many seconds to wait between batches. Since we're generating data in a loop, if we specify 60 for example, then each loop will wait 60 seconds before it loops again. This latency max s is the maximum timestamp lag to subtract from each event, simulating network or processing delays. So let me explain the function body itself, which is here. So this line, while true, creates an infinite loop, meaning that the block under it will run forever until you manually stop it. So we use this datetime.now and then specify the time zone in UTC format to get the UTZ time zone. This ensures that each batch is stamped relative to a consistent clock, and the timestamp is stored to this variable now. We also have this empty data list. This is where we'll append our batch of records. So we're then building the batch of records. So we start with this for loop. We loop once per each device. So we specify a device count in the function argument here, device count. So if we specify 3, then it will loop 3 times, once for each device. TS is simply the timestamp. So it takes this timestamp value now, and then it subtracts the latency. So this will be anywhere between the value we specify. So if the latency we specify is 60, then it will subtract anywhere between 0 to 60 seconds from this timestamp. So this just simulates network or processing lag, because the data doesn't immediately get ingested into the target system. There is usually a little bit of delay. Value is a random number between the low and the high value we provide as arguments here. It's rounded to 4 decimal places. We then collect each record as a plain Python dictionary. So we have device ID, event time, and the column name. So again, we specify the column name as an argument here. Spark can then infer the schema automatically. So as we loop, we're adding each dictionary element into this data list. Once we've completed the loop, we are then creating a data frame out of this data array. And then finally, we're appending the data generated in the current loop to the storage volume, so this path. We're appending it because we've got the mode as append and the format is delta. In the last cell, we're just specifying how long to wait before we loop again. So this is the batch interval S argument here. So if we say 60, for example, it will wait 60 seconds and then it will loop again. So this yields a steady, configurable cadence of data. Because the loop never breaks, this function continuously pushes new, realistic sensor data, complete with intentional timestamp lag, into our landing zone for the rest of the pipeline to process. So now in this cell below, we're actually supposed to be calling the function. What we want is 3 executions of the function to run at the same time. Once for temperature, once for vibration, and once for tilt. Now because this generate stream function is an infinite loop, calling it 3 times in a row would mean that it would hang on the first call, and you never reach the second or third calls. That's why we actually need to launch 3 instances of the generate loop function at the same time. So we need to launch them concurrently rather than sequentially. And that's why we're using Python's thread pool executor. And that's what I'm importing here. It's imported from concurrent.futures. So we simply define all of the variables. So we have device count of 5, meaning that there are 5 bridges. We have a batch interval of 60 seconds. We have a latency max of 60 seconds. And we have 3 streams. Each tuple element contains the delta path, the column, and the low and the high values. Inside this with thread pool executor, we specify the maximum workers as the length of this stream. So there'll be 3 workers because we need to run 3 concurrent streams. And then in the block, we're running a loop. So we are creating a path, column name, low and high variable based on the values in this stream. And we've already defined the device count, batch interval, and latency, so we can actually submit the functions. So this executor.submit invokes this generate stream function 3 times, once per each element in streams. So this pattern simply runs 3 concurrent instances of the generator function, giving us 3 live independent delta streams with no extra orchestration cost. You can review how this thread pool executor works in your own time if you're unfamiliar with it. I'll share a link to some documentation. But within this executor.submit, the first argument is the function that we're executing concurrently, and that is generate stream. The subsequent arguments are the arguments that go into the function call. So each generate stream call takes these arguments in order: path, column name, low, high, device count, batch interval S, and latency max S. So effectively, you're submitting the following functions that you see in this cell below. So you've got generate stream, you've got the path, and then you've got all of the different parameters. This is the low value, the high value, the device count, the latency, and the lag. And you're doing that 3 times. But if you were to just run it like this, if I just uncomment this, if you were to run it like this, what would happen is it would just run this first function call, loop forever, and it would never run the second or the third. So let me just comment this out again. So essentially that is what this thread pool executor is doing. It's just running this generate stream function concurrently, 3 instances of it, and that's what we've configured. Okay, so let's run this notebook. I'm connected to a serverless compute cluster. Please only use a serverless compute cluster if you're using the 14-day free trial. Otherwise, you'll incur higher costs than if you create your own single node personal compute. So let's click on Run All Cells. This cell has run, which defines the function. And this cell below is running. This cell's status indicator will continue in the running state. Behind the scenes, each of the 3 threads is appending new data files every minute into the specified volumes streaming folders. So let's verify this. Let's head over to Unity Catalog. So in the landing schema, we have our volume. Within the volume, we have 3 subfolders. Here's bridge temperature. As you can see, there's now a Delta transaction log and Parquet files that are being added. Same with bridge tilt, and same with bridge vibration. So this is continuously running. As you can see, it continues to repeat every minute. So this ran at 2:35 p.m., then 2:36 for the next 3, and then it will run in 2:37. So it will continuously run in an infinite loop. So we can query the data using the SQL editor. So let's actually query the data in this bridge temperature subdirectory. So I could do select *from, and then it's in delta format. So I could just do delta and then specify the path to the file storage location. So let's run this. So as you can see, we have submitted records for 5 devices. They have a temperature between 19 and 23. And here's the event time. In the event time, we have introduced lag between 0 to 60 seconds randomly. Let's now query the bridge tilt. So I will do select *from delta and then specify the path to the bridge tilt subfolder. So let's run this. So again, there are 5 devices. The event time still has a lag between 0 to 60 seconds, and the tilt angle is between -0.005 and +0.005. Now let's query bridge vibrations. Again, the results are similar, except for we have vibration column with values between 0.005 and 0.05. So the tables will keep growing. Notice there are 30 records returned. If I run this again in another minute, there should be 35 records returned. So let me just try to run this now to see if that updates. So still 30 records returned, but I'll wait. And we can actually just see this here because this is still running. So as you can see, it's still appending the records. So as soon as this is done, I'll query the table again. Okay, so now I'll query the table again, and there should be more records, 35 rows. So this will just continuously grow. So we're now ready to look at the ETL source code for our Delta Live Tables pipeline. Up until now, we've just set up the generation of synthetic data via this data generator notebook. So please just keep this notebook running in the background. Now let's look at our bronze layer source code. So in the workspace, go on O1 bronze processing. This is the source code that we'll use in our DLT pipeline. The source code in this notebook specifically is for the bronze layer processing. So this is where we declare raw streaming tables with DLT's special syntax. So we're defining 3 streaming tables using this @dlt.table decorator. Each definition spins up its own append flow. So DLT handles the continuous ingestion of raw sensor data into our bronze layer. No manual orchestration or checkpointing code is required. So let's break down the syntax of our bronze table definitions. So we first import DLT, and then we use the DLT decorator using @dlt.table. This tells DLT that this function below defines a table in my Delta Live Table pipeline. We specify the name parameter in this decorator, and that is the Unity Catalog table name. It's also qualified with the schema name as well. So we want this table to be created in the O1 bronze schema. This comment is just metadata. We then have this function definition. We define a function. The function name is irrelevant, but it's called bronze_bridge_temperature. It's purely to house the transformation logic. So it returns this stream. DLT reads whatever data frame you return and writes it into the table you named above here. So the function name, like I said, itself doesn't matter. The function returns a streaming data frame. Spark.readstream.format and then .load to the path here, which is bridge temperature, continuously monitors this specified path for new files. So each new micro batch of data is automatically ingested and made available for downstream processing. By returning it from this @dlt.table decorator, DLT automatically spins up an append flow that ingests every microbatch into this bronze table. We repeat the same pattern for bridge vibration. So as you can see, the path is now to bridge vibration and bridge tilt. So the path again is to bridge tilt. So in just a few lines of code, we've declared 3 streaming tables. No manual job definitions, no boilerplate orchestration, just declarative logic that DLT turns into a fully managed pipeline. Great. So let's move on to the silver layer logic. Okay, so let's open O2 Silver Processing. In this notebook, I'm defining all of the transformation for the silver layer. In the top cell, I'm importing the relevant libraries. In this next code cell, we're defining a static metadata table in the silver layer. So again, we're using @dlt.table. So we're telling DLT, create a managed table in Unity Catalog called bridge metadata in the O2 silver schema. And we've provided a comment. We're again defining a function. This assembles a plain Python list of dictionaries stored in a variable called bridges. Each element is a dictionary object. So it contains the bridge ID, the bridge's name, the length in meters, the main span in meters, the height in meters, the location, the type of bridge, and the year it was opened. So we then return a data frame based off this bridges variable. So because this function is decorated with @dlt.table, and it's not reading a stream, it's actually just generating some static data, DLT treats this as a materialized view, or a batch table. It will only run once in our pipeline, write out the data frame, and make it available for downstream joins. In the next code cell, and actually in the remaining code cells, I'm defining streaming tables. Specifically 3 streaming tables, one for temperature, one for vibration, and one for tilt. These streaming tables are created by combining the incoming streams from the bronze layer and this static table defined here, which contains the additional bridge metadata. Again, we start with the @dlt.table decorator. We declare the schema dot the table name, so this is called bridge temperature in the silver schema. We provide a comment as well. Immediately after, we layer on 2 expectations. So these are data quality checks. So we use @dlt.expect_drop, which drops any bad rows before it lands in the table, and @dlt.expect, which simply records the failure in your pipeline metrics rather than dropping it. So these are expectations. They're declarative data quality rules that you attach via decorators that evaluate an SQL predicate. So the name of the check is called valid event time, and the predicate is that the event time column is not null. In this one, the expectation is called valid temperature range, and the predicate is that the temperature must be between -20 and 60. So these expectations give you built-in monitoring and enforcement without any extra Spark code. So then inside the function itself, we do a dlt.read stream to read this bronze table that we've defined upstream. We then cast the event time to a proper timestamp, and then we rename the device ID to bridge ID. We then perform a stream to static join with the bridge metadata table that's defined in the same silver layer. We perform the join on the bridge ID column, and it's a left join. We then select only the enriched columns, so bridge ID, name, location, event time, and temperature. This gives us a clean, validated, and self-describing temperature stream ready to feed into our gold layer aggregations. We essentially repeat the same thing for the bridge vibration table, except for we're selecting the vibration column rather than the temperature column. And then we also have slightly different expectations. So for this second expectation, the vibration must be between 0 and 0.1. And then for the bridge tilt streaming table, again, the expectation is slightly different, where the tilt angle must be between this range. And the last column is tilt angle rather than temperature or vibration. So that's the silver layer processing. We can now move on to the gold layer. So our gold layer processing is in this notebook called O3 Gold Processing. In this layer, we define a single consolidated aggregated table called bridge metrics in the O3 Gold schema. It brings together all 3 metrics from every bridge aggregated over a 10-minute window interval. So here's the definition. Notice we have 3 variables, temp, vib, and tilt. In each of these, we're reading from the silver stream. So for the temp variable, we're doing a DLT.read stream from the bridge temperature table in the silver layer. For vib, we're doing a read stream for the bridge vibration silver table. And for tilt, we're doing a read stream on the bridge tilt table in the silver layer. But what you may have noticed is we're doing a 2-minute watermark on each of the streams. This tells Spark to wait up to 2 minutes for any late arriving events. We may have late arriving data due to our simulated lag. So it will wait for 2 minutes and then it will drop anything beyond that 2-minute window. This bounds the state for our aggregations. As you can see, this watermark is applied to all 3 streams. Further below, we then perform windowed aggregations on these variables. So we have temp ag, vibe ag, and tilt ag. So let me explain temp ag, because the approach is then the same for vibe ag and tilt ag. So with temperature aggregation, we are taking this temp variable, and then we're performing an aggregation. So we're doing a window aggregation on the event time for 10 minutes. So it contains the results from temp and further processes the streams to compute a 10-minute tumbling average of temperature. So as you can see, the aggregation itself is an average on the temperature. VibeAg follows a similar pattern except for it gets the maximum vibration over the 10-minute period. TiltAg gets the maximum tilt angle over that period. So let me visualize how the watermarking feature works. Let's say we have the following data entries. We want to perform an aggregation to get the average temperature grouped by device ID with a 10-minute window and a 2-minute watermark. So for the current data, since we have a 2-minute watermark, we can't yet close the 10-minute window that falls between 1040 and 1050. Now let's say we get another dataset. The event time is beyond the window end time for 1040 to 1050. And in turn, it opens up a new window between 1050 and 11. But we still can't close the previous window because of the 2-minute watermark. This watermark waits to close the aggregation when it receives a data point that has a timestamp of 2 minutes after the end of the window. So why should we do that? Well, the reason is simple. It's to make sure that we're able to wait in case an out-of-order event for the previous window arrives. This can happen in a real-world situation because the arrival of data can be delayed for whatever reason. And we're actually simulating this in our project by introducing a random lag between 0 to 60 seconds. So now let's say we get another data point. The event time is actually earlier than the previous data entry, so it's a good thing we haven't closed the window yet. This record is late arriving. Now finally, we get another data point. This time the event time is 2 minutes later than the end of the 1040 to 1050 window, so we can finally close this aggregation. The next window, that's between 1050 and 11, will only be closed when we get a data point that's later than 1102. So that's how windowing and watermarking works. Okay, so once we've got our aggregations, so we've got our 3 aggregations for each of the stream, we're actually then taking those flows and performing stream-to-stream joins, combining all of the data from the 3 streams. We join the 3 aggregated streams, tempag, vibeag, and tiltag, on the same keys: bridge ID, window start, and window end. This is because all 3 of the streams use identical window boundaries and watermarks, and therefore the join is perfectly aligned and remains append only. So we're still able to create a streaming table even though we're creating joins. So the result of this is a single, continuously updating table that gives you, for every bridge and every 10-minute interval, the average temperature, the maximum vibration, and the maximum tilt angle. We're also retrieving dimensional values such as the bridge ID, the name, the column, the window start, and the window end time. So this gold layer table is ready for real-time monitoring or downstream dashboards. So that's an overview of our code. We can now take these notebooks, bronze, silver, and gold, and use them as source files in our DLT pipeline. Now that I've run through the code, it's time to create the DLT pipeline. So head over to Workflows, and then Create ETL Pipeline. Let's give it a name. I'll call it Bridge Monitoring _DLT Pipeline. I'm going to specify serverless compute. If you don't use serverless compute, then you'll need to configure your compute below here. If you do, please use a fixed size of 1 worker because this is more cost efficient. But since I'm using serverless compute, I don't need to configure that. For the pipeline mode, I want it to run continuously. Now we can select our source code. This will be the path to the notebooks. So I'll be using the bronze, silver, and gold notebooks. So let me select them. So unlike with jobs, we don't need to create tasks for each notebook. The system will automatically figure out the lineage and dependencies along with the order in which it needs to run everything, simply by analyzing the source code that we provide. So that's what I mean when I say DLT is a declarative process. We defined our tables and the system will determine the lineage and return the DAG. So now we can specify the catalog. The default catalog is this bridge monitoring catalog. For the default schema, it doesn't really matter what we provide. So I'll just specify default. The reason it doesn't matter is because I've already qualified the schema when it comes to the table references. So DLT will know which schema to populate the table in. So we've set everything up. We can now create and start the pipeline. So it then will take you to the pipeline UI. In this central pane, it tells us which step we are in the process of actually creating the pipeline. It will soon convert into a lineage visualization consisting of tables laid out as nodes in a directed acyclic graph, with arrows showing the dependencies. We have an event log here in the bottom, and on the right, we have the pipeline details and the update details. So the pipeline itself will be continuous. We can stop the pipeline by clicking here on stop. So let me just wait for the pipeline to finish. So as it builds the flow, so if I just expand this, we can see various metrics. This green dot represents the number of records that have been written. This grey dot represents the number of records that have been dropped. So as you can see, 35 records have been written in this bridge temperature table. If you click on any of the nodes, you can see additional information, such as the data quality, the schema, and the flows. Please note that for me, the bridge temperature table contains fewer records than the bridge tilt and the bridge vibration tables. That's because I've had to go back and delete some records from the old tables. But for you, you should be seeing similar numbers across all of the layers. The reason that I don't have any records in this bridge metrics table yet is because it has a 10-minute aggregation window with a 2-minute watermark. So it will only close the aggregation once that time has elapsed. So as the pipeline continues to process and append new data that's generated by our notebook, we can query these tables to analyze the data as it's being generated. So I've got some queries on the screen here. They will simply return all of the tables in our project ordered by either the event time or the window start time. So let's query this bronze bridge temperature table. So here are the records. So we've got 40 rows returned. Since it's ordered by the latest event time, we can see the latest event time belongs to this device ID of 4. So if I query this silver table, I should also see a device ID of 4. Here it is. And it should have the same event time. It also contains additional information such as the name and the location. We can do the same for this bridge tilt table. So this so far contains 85 rows. The latest record processed was for device ID 2. The tilt angle was negative 0.0038. So let me query the silver bridge tilt table. And here is the same bridge ID. So this used to be device ID in the bronze layer, it's been changed. And here's the tilt angle. We can see it relates to a bridge in Lisbon, Portugal. And this is for bridge vibration. The latest record received is again for device ID 2, and here's the vibration recorded. And we can see that that should flow through to the silver layer as well. Indeed, it has. So every time I query these tables, as long as a minute has elapsed, it should process new records. So let's query the gold table now. Here it is. This gold table is currently empty. The reason it's empty is because it has not closed any aggregation window yet. So let's see what the latest record is for bridge temperature, for example. So the latest record received was for 2:27 p.m. Currently the time for me is 2:28. So this window isn't expected to close for another 5 minutes or so. And we can see that here. Or actually the window has closed now. So it must have closed a previous window. So now if I query the gold table, it should show some data. As you can see, it does. So the window that it closed was from 10 past 2 to 20 past 2, as you can see from the window start and the window end time. So the pipeline is working nicely. We can also put it to the test. So if you recall from the source code, so if I actually just click on the pipeline, you can click on any of the source code here. So in the source code for the silver processing layer, we created some expectations. So for the bridge temperature table, for example, if we get any records where the event time is null, it will drop that record. So let's actually insert a record manually that will make it drop this. So let me go to a new query and I'll paste in some code. So what this is doing is it's inserting into this storage volume path, which is bridge temperature, the value is 1, null for the event time, and 20 for the temperature. So let me run this. So we'll insert that record. Okay, so now let's go to the pipeline. So under workflows, here's the pipeline. We should see in bridge temperature, that record should have been inserted. So let me actually just expand this so you can see. So we've got an extra record here. And in bridge temperature, we've got this warning, dropped record. So if I click on data quality, we can see this valid event time expectation was failed. So the record was dropped. So going back to queries, if I actually query the volume, so the landing volume for bridge temperature, we should see the record where the event time is null. Here it is. But in the silver layer, so if I query this bronze temperature table for the silver layer, we will not be able to see it because it's been filtered out. So our pipeline was successfully able to drop the record that did not meet that expectation. But we also have another expectation we defined. The next expectation was that the temperature range is between -20 and 60. So let's put this to the test. But this time it won't drop the record, it will just display as a warning in the pipeline. So I will go back to that cell and I'll paste in this line. So let's run this. It is putting in the temperature of 65. So let me change the time to be more accurate to the current time. And run this. Okay, so that's been inserted. So now let's monitor the pipeline. So let's go to workflows. Here's the pipeline. And now we can see that the record was processed because there's 77 written records. So let's click on bridge temperature, go to data quality. If we go to expectations and all, we can see that it's not a failure, but it is documented that this valid temperature range expectation was exceeded. And if I go to this query pane and query this silver bridge temperature table, we can see that that record still made it through. So the pipeline is working exactly as expected. It will continue running until we manually stop it. All right, so that wraps up our DLT streaming pipeline. Let me recap what we've done. We started by spinning up 3 continuous data generators to simulate temperature, vibration, and tilt readings with real-world timestamp lag. So as you can see, this is still running. So there have been 50+ statements executed so far. This is continuously writing data into this landing volume called streaming. So this is continuously being updated. In the bronze layer, we ingested those data streams from the volumes, and we created 3 streaming tables in the bronze layer: bridge temperature, bridge vibration, and bridge tilt. In the silver layer, we joined each of those streams from the bronze layer with this static metadata table we created in the silver layer, as well as applying DLT expectations to drop bad records and enforce value ranges. So the resulting tables, bridge temperature, bridge vibration, and bridge tilt, in the silver layer contain enriched data with bad data that's been dropped. And then in the gold layer, we applied 2-minute watermarks, computed 10-minute tumbling averages, so average temperature, peak vibration, and peak tilt, and used stream-stream joins to consolidate all 3 metrics into a bridge metrics table. And then Delta Live Tables pipelines handled the orchestration, the automatic retries, the incremental processing, and the data quality enforcement without us having to configure it. We simply declared what we wanted to do in our source code. So with our pipeline continuously running, we can query any of these tables using Databricks SQL, build live dashboards, and set alerts on any anomalies. Just to emphasize, this is not an exhaustive tutorial. There's a lot more you can explore with DLT, from CDC flows to custom expectations to advanced monitoring. So I encourage you to fork the code in my GitHub repository and continue experimenting and building your streaming ETL skills. Please also check the video description for the repository links, additional documentation, and resources to help you dive deeper into this topic. Before you wrap up, please manually shut down this pipeline. Otherwise, it will continue running indefinitely and potentially incurring costs. So click on Stop. Since the data generator notebook is continuously running as well due to the thread pool executor, you'll also have to interrupt that execution. Otherwise, this will also keep running in the background. Great. So thanks so much for watching this video. If you enjoyed this deep dive into DLT, then please like, subscribe, and hit the bell icon so you don't miss future end-to-end projects like this.